Let's start by looking at how displacement changes over time, which helps us understand motion. The graph here shows displacement on the vertical axis and time on the horizontal axis. When the line is steep, like at the beginning, it means the object is moving quickly. This is high velocity. As the line becomes less steep, the object slows down, indicating low velocity. When the line is flat, the object isn't moving at all and is stationary. The key concept here is that the slope, or gradient of this graph, which is the change in displacement over the change in time, represents the velocity. This means velocity tells us how fast and in what direction the position is changing over time. Understanding this sets the foundation for interpreting movement in terms of position and time.
When we look at this curve, the key thing to notice is the gradient, which tells us about the velocity. A steeper curve means the velocity is increasing, and that's what we see here as the gradient grows bigger over time. This means the object is speeding up, not moving at a constant rate. The curve itself is bending upwards, which shows this changing velocity. If the gradient were getting smaller instead, that would mean the object is slowing down, or decelerating. So by observing the steepness and shape of the curve, we can understand whether the motion is accelerating or decelerating.
Here we see how velocity changes over time, first increasing steadily and then leveling off. The upward slope shows uniform acceleration, meaning the velocity is increasing at a consistent rate. This rate of change in velocity over time is called acceleration, which we can calculate using the gradient of this line. After 5 seconds, the velocity becomes constant, indicating zero acceleration during this period. This part of the graph represents motion at a steady speed, where velocity does not change with time. So this graph clearly illustrates the transition from accelerating motion to constant velocity. Looking at this velocity time graph, you can see how velocity changes over time in both positive and negative directions. The velocity starts off positive, but decreases steadily, indicated by the downward slope of the line. This slope is called the gradient, and because it's negative here, it means the acceleration is negative. Negative acceleration simply means the object is slowing down, or decelerating, in the positive direction. Once the velocity crosses zero and becomes negative, the object is moving in the opposite direction. So, a negative gradient always shows deceleration, regardless of whether the velocity is positive or negative. This helps us understand the relationship between the direction of motion and changes in speed.
Here, we see how the area under a velocity time graph can represent displacement. The graph is divided into two sections, Area 1 and Area 2. We calculate displacement by finding the sum of these geometric shapes. In this case, a triangle for Area 1 and a rectangle for Area 2. The logic behind this is straightforward, because velocity multiplied by time gives distance, so the units check out as meters. By adding these areas together, we determine the total displacement during the return journey, showing how the mathematical concept connects to the physical movement depicted on the graph. Here we see how displacement is calculated from velocity over time by looking at the areas under the curve. The blue shaded region, Area A, represents positive displacement where velocity is above zero. The gray shaded region, Area B, represents negative displacement when velocity drops below zero. To find the total displacement, we subtract the negative area from the positive area, effectively summing the algebraic areas. This means the final position depends on both how far and in which direction the object has moved, relative to where it started. By combining these areas, we get a clear measure of net displacement over the entire time period. Displacement changes with time, and the rate at which it changes is called velocity, which we find by looking at the gradient of the displacement time graph. Conversely, if we know the velocity over time, the area under that velocity graph gives us the displacement. Similarly, velocity changes over time, and its rate of change is acceleration, which we determine by the gradient of the velocity time graph. This means acceleration is the gradient of velocity, and velocity is both the gradient of displacement and the area under the acceleration graph if we had it. Together, these relationships form the core of how we analyze motion using kinematics, connecting displacement, velocity, and acceleration through gradients and areas under graphs.